Okay, just waiting on like one or two more people. For the credit rescue days next week, do we need to attend class? No, you do not need to attend class. However, I believe so. I think you still have to attend class until the Wednesday next week, right? So you want to attend until the Wednesday next week, and then 24, 25, 28, you don't have to come to class, I don't think.
So, Mister, the last test we will do is the last test we did, right? That's the last test we're gonna do, or?
Yeah, and then the only thing left now is your poster, and that's it.
Oh, okay, thank you.
No problem. Okay, looks like we're all ready to go. All right, let's get started here. So solving financial problems involving exponential functions, not always, not only exponentials, but it does include powers in it, which is why it mentions exponential functions. And so that's why we do this right after the exponential functions unit. And we usually leave financial math, or I usually leave it to the end because I think it's the most useful, and it just kind of sticks in your head a little bit. And even if you don't get the specific math for it, at least you're understanding the different options that you have, and how things work. So let's dive deep into this. So percents and decimals. So we know that percent means out of 100. So if we have like 64%, that's 64 out of 100. So to convert a percent to a decimal, we move the decimal places 2 spaces to the left and remove the percent sign. So if we have 64%, we do 64 divided by 100, which gives us 0.64. Or you just move the decimal place 2 spaces to the left and get rid of the percent sign. Just like that. So when it asks us to convert each percent to a decimal, right? Of course, there's 2 ways to do it. You can do 7 divided by 100. You divide by 100, and that's going to give us 0.07. When you have something like this, you have a quarter, right? Solve the quarter. So convert this first to 6.25%, and then you can divide that 6.25 by 100, and you get 0.0625 as your decimal. And there it is. Then we have 0.5%. Once again, doesn't matter if it's a decimal. If it's a percentage, you can always divide by 100. That's going to give us 0.005. And what about this last one? 0.008 divided by 100. What does that give us? Anyone? 0.0008. Yes, thank you, Kimberly. Very good. 0.00008. Pretty easy, right? Converting percentages to decimals. The reason why we do this is because we never use percentages in our equations. I want you guys to keep that in mind. When you calculate tax and stuff, like in Ontario, we have 13% tax here, right? On all the things we buy. When we calculate tax, we don't use percentages. We use the decimals to figure out how much the tax is. So always keep this in mind. The percentages is used to kind of represent something, but when you're plugging it into a formula or an equation, you want to convert it to a decimal. Or not want to, you have to convert it to a decimal. We never, ever, ever use the percentages in our formulas. Okay? So please keep that in mind. So then, when you find a percentage, right? When you find a percentage of something, the word of means to multiply, right? So if we say 12% of 150, we're multiplying 12% to 150. But like I said, if we're using it in math, we don't use percentages as percentages. We use percentages as decimals. So we have to convert 12% to 0.12 and then multiply to 150. That'll give us 12% of 150. Okay? Any questions? So if we try to go here, 7% of $250, convert the 7 to 0.07. Of means to multiply. I'm just going to use the my dot in the middle. And then times 250. And that's going to give us our final answer. So multiplying that on my calculator here, I get $17.5 or $7.50. When you multiply a percentage to a value and it has a unit, that unit stays. So since it was $250, we're talking about dollars still, right? If we're finding a percentage of something, we are working with dollars. Same thing for the next one here. 3.5% of $127.79. Try this one on your own. I'm going to give you a minute to calculate it, and then we'll take it up. Okay. You should be finishing off the calculations here. First step, change the percentage to a decimal. You should have gotten 0.0035. Oh, sorry. 0.35, sorry. So 0.035 of means multiply 127.79 and multiplying that out. You should have rounded it to 4.47. Don't write any more decimals. Why? Because since we're talking about money, we only have until the cent, which is the second decimal place. So we don't want to write more decimal places. We just want to round up to the second decimal place. Okay? This next one here, calculating tax. So like we said, in Ontario, we have 13% tax, right? How do you calculate that? Well, you can do 13% of the item and then add if we want to find total cost, or you can do another value, which is 113%. So let's talk about it. I'm going to talk two ways that you can calculate this. One way is faster than the other. So the first way is to say, oh, I'm going to find 13% of $16.99, which gives us 0.13 times 16.99. And that's going to give us 2.21 rounded. Okay, $2.21. Then the total is going to be 16.99 plus 2.21 because we got to add to our cost, just like it does in real life. So then we're going to get $19.20. Right? So this is one way of doing it. The second way of doing it is not finding 13%, but 113%. Why would I do 113%?
Because 100 is 16.99 and plus 13% in this, like,
Yeah, absolutely. So exactly what Sophia said, 100% represents that 16.99. That's the total cost of, or that's the original cost, and then we're adding an extra 13% to it. So this skips over that adding part that we did on the left here. So when we change this to a decimal, we get 1.13 times 16.99. And when we do that, we get rounded $19.20, which is exactly the same. So this, on the right side, when we're calculating the total cost, right, we can just use 113% because we're adding 13 to the original price tag. Please be careful what the question is asking you. Sometimes I just ask for tax. Sometimes I ask for total cost. Make sure you pay attention to what I'm asking for. All right. Any questions here about percentages and decimals? Hopefully it's so far so good. That pushes us into simple interest. So simple interest is money earned or owed only on the original amount invested or borrowed. So what does that mean? Well, if I say, oh, I put $1,000 in the bank, and the bank gives me like 2% interest, then I'm only getting 2% of $1,000 every year, rather than 2% of my new amount every year. Right? So that's simple interest. So this is simple interest. And so the original amount invested or borrowed is referred to as the principal amount. This is important here. Okay? Or we call it the principal. Okay? So our starting value is called the principal, and I'm going to be calling it the principal from this point onwards. Okay? So I'll ask you, what is the principal? What is the principal? What is your starting value? That's what I'm asking for. Okay? So it says, suppose you invest $1,000 in a bank that offers you 5% simple interest. What is the ending balance after 5 years? Well, let's consider 1 year. So 5% is 0.05. And so if we find 5% of 1,000, we get $50. So the interest for 1 year is going to be $50. So every year I'm going to get an extra $50 into my bank account for simple interest calculations like this. Okay. So when we complete the chart here, just like we did before, so now on year 2, we have 1,050 in our bank account, but the interest only calculates from the 1,000 that we started. So if we do another 1,000 times 0.05, we're going to get $50 again, which means at the end of the year, I will have 1,150. That looks like 150, so I'm going to fix that. Okay, so we have $50 here, $1,100 here. Oh my gosh, I am all over the place, guys. I'm so sorry. Sorry, fixing that real quick. 50 plus 1,050 is 1,100. Okay, from that point on, year 3, right, we got 1,100. The balance is calculated on 1,000. The interest, I think you realize, is just $50 now every time. It's always going to be 50 because we're only calculating on the original amount, which means $50 on top of what we started is 1,150, which moves on into the next year, which gives us 1,200, which moves us on into the next year, which gives us 1,250. Right? So simple interest, this should seem weird to some of you. It's like, why would it not use the new value? But that's the weirdest one, right? That's weird with simple interest. where simple interest just uses your very starting one to calculate your interest forever. So that's simple interest. Okay. So instead of doing a table of values, right? Instead of doing a chart like this is a pain. So now we're going to use the formula, or we're going to learn the formula. So the formula is I is equal to PRT, where I refers to the interest, P refers to the principal, R refers to the rate, and remember, the rate has to be in decimals, because the rates are going to be given to you as percentages, so we want to make sure that it's in decimals. And T refers to the length of time in years. Okay, so I is equal to PRT, or P times R times T. Okay, so for example here, if we plugged it in using the formula, our principal was $1,000, rate was 5%, and if we said 1 year, it would be $50. If we do 5, it would be $250, so on and so forth. So this calculates just the interest. So if it's asking for the final amount at the end of however many years, you got to add it to the principal. Okay, so we want to make sure we do that. All right. Any questions about simple interest here so far with like formulas and the explanation here? Okay, no questions. We're going to move on. And then the next thing, which is what most banks do, is compound interest. So compound interest is a little bit different. You earn money, or you earn interest on the new ending balance every single year. So whatever money you end with is the amount, the interest is now applied onto the new amount rather than the starting one. So for example here, if we start once again with $1,000 in the bank with a 5% compound interest, this is what's going to happen. So the first year is the same. We're going to get $50, right? Because 5% of 1,000 is 50. But then at the end of the year, we get 1,050 as we go into year 2, which means our new amount, which is 1,050. So when we calculate that, 1,050 times 0.05 times 1, because we're doing the 1 year, right? We're going to get, oh, look, a little more interest than before, 52.5. Then we add it on to our starting balance here, and we're going to get $1,102.50. And so that new ending balance becomes our new starting balance. And I think you guys can see where this is going. The interest will apply to our new starting balance, and you start calculating the rest. So if we calculate the new interest again, here, we get $1,102.50 times 0.05 times 1. And we're going to get 55.13, rounded. And so 55.13 plus 1102.5 is going to give us 1,157.63. And so on and so forth. So we're going to keep going with that and continue onwards here. So I think you can see that, yes, compound interest is better in terms of making money, because our interest is getting bigger and bigger the more we save. If you remember that, if those of you who were at Brook for a while, we had that funny money presentation. If you guys remember that, like assembly, that funny money assembly where like this guy came in and he was talking about like investments and all that kind of stuff. I don't know if you guys remember. And remember how I was talking about like how if you save like $200, every year or every month for like the next 30 years, you could easily become a millionaire. That's kind of like the idea of compound interest, how it kind of works upon that. Compound interest does help. It's more so that saving money every year is going to help a lot. But compound interest is a benefit out of that because the more money you add in and the more money you have, the more interest you're making every year because it doesn't depend on your starting value. So if we continue onwards here with like 1157.63 times 0.05 times 1. And so our new interest in the fourth year is 57.88. So I think you guys can see what's happening here. The interest is growing, like it's consistently growing every year because we have more money. And so we add that on to our final value that we had, and I get 1,215.51. In comparison to simple interest, we already have more money. We have around $15 to $16 more than someone who just had simple interest, which might not seem like a lot, but it adds up. And so you can see compound interest definitely gains a little more interest than we think. So obviously, which one would you pick? Simple or compound interest? You can type it in chat. Which one's obviously better to save money or save more money? Yeah, compound interest is definitely the way to go. And that's why banks give compound interest. So banks don't actually give simple interest. It's all compound interest. It's based on how much money you have in your account, and you get paid interest from that value. Okay. So to summarize it, simple interest, money earned or owed only on the original amount. Compound interest is money earned or owed on the original amount plus anything that's added on from there. And then we have our four things here. Principal means the original amount of money. Rate is the interest rate as a decimal, is really important. Term is the time, right? How long it takes for the investment or how much you borrowing the money. And per annum. Annum here means year. It's per year. So financial like institutions and stuff use different words. Annum comes from the word annual, which is year, right? So annual celebrations means like a celebration, a yearly celebration. So annum comes from the word annual, which is per year. Okay. So then we go over some of the problems here. So question 1, you invest $250 per 4% at 4% per annum at a bank that pays simple interest. So how much interest would be earned each year? So if we calculate that using our interest formula, since it's asking us how much simple interest, we just use I is equal to PRT, which is equal to 250 times 0.04, because it's 4%, times 1. And so 4% of 250 is $10. So you're making $10 of interest every year. Very simple. If you kept your money invested for 8 years, what is the total simple interest that would be earned? Well, we just use the same formula if we wanted to here. So 250 times 0.04, and this time we do it by 8. And of course, if you realize, well, we have the interest for 1 year, can't you just multiply that by 8? It's like, yeah, you can do that. It's exactly the same. So you should get $80. And then the question is, how much money would be in your bank account after the 8 years if you didn't take out any money? So then your total amount, right, would be 250 plus the 80, right? Because you have 250 and we add the $80 of interest, which gives us $330. Okay. So notice how in these questions it says interest, like it asks for total interest compared to money in the bank account, right? Total amount. So make sure you read carefully about what the question is asking for. So continuing onwards here, number 3, this time is compound interest. So for compound interest, how much would be earned in the first year? And so, okay, let's figure out compound interest here in the first year. Once again, this doesn't change. For the first year, right, we're still using our simple interest formula to calculate for year 1. So it would be 750 times 6% times 1, which gives us $45 within our first year. However, for the second year, the principal changes. So since it's compound interest, the way we calculate interest in our second year is going to be the fact that our interest is now not using 750, we're using 750 plus 45, which is 795. And then 6% of that. And that's going to give us 47.70, right? So how much more compound interest is earned? Around $2.70. We're getting a little bit more in our second year, right? We're getting a little more interest as a result. Okay. Now, question C and D would be a pain to do for now because it's a chart. Like you want to complete a chart and do that. So instead, this pushes us into 8.2. All right. So most of you are probably thinking, Mr. Choi, this is a really big pain to calculate compound interest this way. Like having to like calculate the new principal every year, multiplying by the rate. That seems so redundant. That seems so messed up. Is there no other way we can do it? And the answer is, well, yes, there is another way we can do it, which pushes us into 8.2. So in 8.2, once again, let's talk about simple and compound interest once again. We have our simple compound interest here. The first difference is always going to be the 50, right? Every year we get $50 more. Okay. And for compound interest, which is a little bit different, for first differences here, we got at the bottom there 1276.29 minus 1215.51 gives me 60.78 here. And then we have 1215.51 minus 1157.63, which gives us 57.88. And we continue on calculating the rest of these. And then the last one, 1102.5 minus 1050 gives me 52.5. And if we try to calculate the second differences here, we get 2.9, 2.75, and then 2.63. So you'll notice that the second differences don't match. So in our first one here, the first differences in our first one, it's linear. It's a linear relationship. But in our second one, it's not even quadratic or linear. It is exponential. We see a specific change here because of how compound interest works. And so we're kind of showing you here, right, that little relationship difference. Okay, so we're just going to jump right actually down here to simple interest and compound interest graphing here, just to see visually what they look like. So for our simple interest, as we look at our table above, we start at 1,000, then it's 1,050, 1,100, 1,150, 1,200. And of course, if we had year 6, it would be 1,250. So we have year 1 is 1,000. Year 2 is 1,150. Year 3, 1,100. Year 4, 1,150. Year 5, 1,200. Year 6, 1,250. So that would be our graph here. That looks linear to me. Looks pretty good. For our compound interest, a little bit harder to graph. So we have 1,000 at year 1. 1,050 at year 2. And then we have 1,102. So it would be a little bit higher, right? And then we have 1,157, which would be a little bit higher once again. 1,215, which is a little bit higher. And then 1,276, which is much higher than what we expect. Okay. Now, yes, both of these look similar, I know. But for compound interest, there's actually a little bit more of a kind of like a curve upwards. Well, this is a completely straight line, right? It doesn't look significant now because we are not working with big numbers here, right? And so as we continue on and we try to graph like these relationships here, and we can indicate the graph here like a nice straight line like this, which allows us to find the ending balance at year 10, which is the next question here, right? And so for simple interest, it would be 1,450. Okay. For compound interest, it's a little bit harder, right? But the ratio that's going to be consistent for compound interest is going to be sorry. So what is the value of the constant ratio for the compound interest example? And what seems to be the relationship between the constant ratio and the compound interest rate? Well, we are adding the 0.06, the 6%. It's always the same, right? So it's 6% here, which is the same. The constant ratio and the rate are the same. So that's the important part here, understanding that the ratio or the rate on which it's increasing is always going to be the 6%. That's the consistent one, right? It always goes up 6% from the previous value. And so it's going to be the same ratio all the way through. Okay. Let's see here. Uh, okay. So for the exponential growth for compound interest here, we have our formula. So we have, exponential growth. That should be 1 plus r. I'm so sorry. That is an error. Growth should be 1 plus r. So if this is our formula for exponential growth, then our ratio or our compound interest can be used or can be determined using this value here. So use the following variables. A is the final amount, P is the initial amount, I is the interest rate, N is the number of times, which means using this formula, I think you guys can see here, right? If we are calculating compound interest, the interest would be dependent on the principal amount with the rate times, the rate as I want I here. Sorry. The final amount times the principal, 1 plus I, which is the interest rate, to the power of n. And so A is final amount, P is principal, I is the rate, and to the power of n. Some people don't like this because they're like, why do we have to use I? Can't we just use R as rate? It's like, yeah, I don't mind if you use I or R. Both are fine. But you'll notice that it's the exact same formula as we used before in our previous test, our Unit 7 test, which is just exponential growth. The rate is exactly the same. So we're using this concept of exponentials in compound interest. So instead of drawing that table and calculating the interest every single year, because that's a pain, instead we can now use this formula to find out what my final amount would be after a certain amount of years. Okay? So when we talk about compound interest, when money is borrowed or invested, the interest is added on to the principal after a previous set amount of time. And after that time, the interest is calculated again, and then it's calculated on the new amount, and it keeps going forever and ever. There's another way we call it, which we say is FV and PV instead of A and P. And the reason why is because the other way we call this is called the future value, or what the value is going to be, and then the PV, which is the present value, which is the money you have now. And so that's essentially what's happening with our like compound interest and stuff like that. So both formulas are exactly the same. They mean the exact same things. So don't worry. Just pick one that you like to use. But one thing that you have to note is I is equal to R over N. Okay? It's equal to R over N. And the reason why it is this is because R would be the rate and capital N would be the compound period. We saw this example, or we saw it in our unit test or in our unit practice test, and it's these words right here. Okay? If it's annual, it's once a year. Semi-annual, twice a year. Quarterly, 4 times a year. Monthly, 12 times a year. Bi-weekly, 26 times a year. Weekly, 52 times a year. Daily, 365 times a year. So remember, the whole idea here was, hey, we need to make sure the units match. The time has to match, right? If I'm talking about yearly, then we have to work every year. If I'm talking about quarterly, then we have to talk about that. So making sure the units of time match is really, really important. And so this is going to be your little thing for calculating the number of years. This is good to have for you in the future as well. When you get a job in the future, most jobs pay bi-weekly, which is you get paid every 2 weeks. So you get paid 26 times a year, for example. So these words are often used in finance, in life. So it is something to keep in mind if you guys want to kind of like snapshot this and just kind of keep it with you to use. It's always a good idea. Okay. And of course, the value of n here inside the formula, lowercase n, also has to be in the correct units. So if I'm talking about like semi-annually, right, and you're paying it twice a year, then you got to multiply it by a certain amount, right? So if it's, oh, I get paid twice a year, then how many times does it happen per year? You multiply it by the number of years. So if it's 2 years twice a year, it'd be 4 times. 2 times 2 is 4. Any questions about this? I know this formula and stuff like that seems kind of nuts. Okay. So let's go through some examples of the compound interest. So once again, we're going to determine the values of P, N, and I in the formula for each one. So it says here, Mary invested $500 for 5 years at 8%, compounded semi-annually. Okay? Semi-annually. So for our principal, it is still $500. Okay? Our N, our Yes, our interest rate here, remember, it's R over N. So our rate is actually 0.08 divided by semi-annually, which is 2. So that's what we're going to be doing here. That's actually going to give us 0.04. And our N value, the number of years, is going to be 5 times 2, which is 10. Any questions?
Why do we divide it by 2 again?
Because it's happening semi-annually, and it says it's 8% for 5 years, we're dividing it by 2 because it happens twice a year.
And multiply by 2 because...
And so since it's 5 years and it's twice a year, we multiply it by 2 to get 10. So it's 10 times happens over 5 years. Okay. And then same thing for this next one here. Let's try this one. Principal is 300, which means the interest rate. We look at the rate and we look at how is it compounded. So 5% is 0.05. We divide it and it's quarterly, which is 4 times. And so we're going to divide that out. So times 4. Or sorry, divided by 4. I don't know why I did times 4. Divided by 4, I get 0.0125. And for our N value, we take the number of years and we multiply it by our compound, which is 4, which gives us 12. So it's 4 times per year, and for 3 years gives us 12 times in 3 years. So that's the idea here. Okay. So I'm going to do this first example 2 with you now using these values here, and then we're going to be talking about example 3 as well. Okay. So example 2, Renata invested $500 at 5% compounded monthly for 4 years. what will be the investment be worth at the end of the 4-year term? Okay. So principal is 500. We write down our givens. Our interest rate is going to be 5% or 0.05 divided by 12 this time because it's monthly. And that's going to give us 0.00417. And our number or our duration is going to be 4 years times monthly, which is 12, which gives us 48. Okay. And so in doing so, we get to plug it into our formula. A is equal to 500 times 1 plus 0.00417 to the power of 48. And you calculate that just like you did before, using your calculator and your exponents. And since it's to the power of 48, you better be using a calculator. I don't think you can calculate that in your head. I definitely can't. I'm not a calculator myself. So I'm going to be using my phone calculator here. So to the power of 48 times 500. And I get $610.54.
Yes, sir.
So, yes.
Is it correct if I rounded off the decimals to 0.0042 instead of 0.00417?
Sorry, could you repeat that?
Is it okay if I rounded off the decimals and write 0.0042 instead of 0.00417?
That should be fine. The reason why I didn't do it to 4-2 is because see how it's the 6 that's repeating? So usually we take, for the repeating number, we round to the number that's repeating.
Okay.
Just to make it more accurate, yeah. But the 0.0042 is fine. Okay. Any other questions? Yeah, it's not 4.12, that's 4 times 12.
So if I use the 0.0042, I got a different answer, which is 611.42. Is it okay?
Yeah, that should be fine.
Okay.
That's completely fine. It's just a slight difference. Okay, any other questions? Okay, looks like there are no other questions. Then we're going to move on. Last one here that I want you to do, and we're done our lesson today. Example 3. Try this one on your own, and we're going to take it up. I'm going to give you around 3 minutes to solve it. Tony, if he invests $2,500 compounded bi-weekly for 3 years, it should be worth $2,904.17. Estimate the annual interest rate. So careful with the values that are given to you here. How do you isolate I was the question that I got here. As of now, you do not know how to isolate I. But remember, when it gets to this and you get to the power, I said you need to try to estimate what that value might be. If you have a root function on your calculator, this becomes a lot easier. Yeah, it becomes a lot easier if you have a root function on your calculator. If you don't have a root function, you're gonna have to guess it. For those with a root function on their calculator, you are able to do that on your calculator. I'll show you what I mean on very shortly. Okay, just another minute to finish off. Okay, so if you plugged it in correctly, this was slightly harder only because, once again, finding I might have been a little more difficult for people that don't have a scientific calculator. So your principal is 2,500. Your interest rate you don't know. Your N is going to be 3 years times biweekly, which is 26, which gives us 78. And then our A value, we should write that down, is actually 2,904.17. By doing this, we get into our formula, 2,904.17 is equal to 2,500 times 1 plus I to the power of 78. Dividing both sides first by 2,500 to get rid of the 2,500 on the right. And that's going to give us 1.161668 is equal to 1 plus I to the power of 78. Now, if you have a scientific calculator, you should see a button that looks like this. This is called the X root button, right? Or the nth root button. This is very useful. To get rid of your exponent, you do the nth root, which is, this case, is the 78th root to get rid of it. Okay? That's going to allow you to get rid of that exponent, and that actually gives you a value where 1.001923 is equal to 1 plus I. If you do not have this nth root calculator button, that's not good. You had to guess, which is not exactly the most ideal situation you want to be in. So you would have to figure out what to the power of 78 gives you 1.16 approximately. So if you did, right, if you started plugging in numbers and try to find it out, it gets really hard. You should have gotten like around 1.002, right? It's a pretty small number. It's hard to guess. That's why a scientific calculator is very useful here. If not, you can go to Google and you can actually type the 78th root of this, and that actually gives you your value. So notice how I typed in Google 78th root of 1.161668. It'll actually give you that 78th root. So Google is your best friend in case you can't calculate it. This helps a lot with your interest rate. So that gives us 1 plus I. We have to subtract 1 on the left side. So we're going to get 1.001923 minus 1 is equal to I, which gives us 0.001923 equals I. Am I done? No, because I is equal to R over N. And we want the annual interest rate, not the compound interest rate. So we actually have to do a little bit more here, which is 0.001923 is equal to R over 26. And you have to multiply that out. And that gives me approximately, actually, 0.05% rounded. Yeah, 0.05 rounded, which means the rate is 5%. The annual interest rate was 5%. So the difficult part of this question, once again, if you are unable to do the 78th root on your calculator, you do need to use Google, because Google will help you calculate the 78th root of 1.16, for example. So that's how you get rid of exponents. You have to do the nth root. Okay. And that